So hey guys, what's up? This is Subham Agrawal. So welcome back to my YouTube channel. So today we are going to talk about BIRCH reduction. BIRCH reduction. Okay. So BIRCH reduction is actually a reduction process, and the reducing agent is sodium liquid ammonia. Sodium liquid ammonia. So sodium liquid ammonia forms solvated electrons. Okay, solvated electrons, and these electrons will reduce our substrate. Okay, this solvated electron will reduce our substrate. So how? Let's see. First, let's understand about solvated electrons. Okay, so here it is a vessel, and this sodium atom releases electron very easily because of low ionization energy. And when this electron, actually this whole process is occurring in this vessel where we have the solvent. Okay, so in the solvent, when this electron goes, then this electron would be surrounded by solvent molecules. Okay, so here I am showing here that this electron in surrounded solvent molecules are there, and this overall we say that this is solvated electrons. Okay, and this SOLV is actually the full name of solvent. Okay, that's why I have written it down here. Okay, so this solvated electron will reduce our substrate. See, we can have metal, alkali metal as well as alkaline earth metal. Alkali metal means sodium and potassium, which are 1 electron donors, as well as we can have magnesium and calcium, which are alkaline earth metals. They can donate 2 electrons. But in the BIRCH reduction, we use sodium, that means 1 electron. Okay, yeah, so we use sodium, which is 1 electron donor, and liquid ammonia will be the solvent where our sodium will donate 1 electron, and that electron will get solvated, and actually it will reduce our substrate. Okay, so let's see how this reaction goes. So first let's talk about that freshly prepared, we use freshly prepared reagent. That means we, at the time of experiment, at the time of reaction, we prepare this reagent by our own. Okay, so in the examination, in the entrance examinations, the questions have been asked where it has asked about the reagent. Okay, so let's talk about little bit about the reagent. So reagent is actually of blue color. If you prepared it fresh, then it would be in blue color, but keeping it for a long time, it will turn out to be a brown color. Okay, and since there are unpaired electrons, that means free electrons are there in the solvent, we turned it as a paramagnetic. This electron will turns out to be a paramagnetic. Okay, now see the reaction. And the two things which are I had written in the top. So we will read it after. We will read it. Okay, so now see, there could be a two substrate would be possible. One, that is the group which are being associated with the benzene ring are electron donating group. OCS3 is electron donating group. Okay, the other condition would be where we have COOH it is actually electron withdrawing group. It is actually electron withdrawing group. So we will see the reaction Birch reduction in the both cases. Okay, in the first case and in the second case. Okay, so this is the reagent, sodium in liquid ammonia, and in short, here I can say, or say the final product would be like this. In terms of electron with donating group, the one double bond will get reduced. Try to understand, in your substrate there are the 3 double bonds are there. There would be 3 double bonds are there, while in the product you can see that there are only 2 double bonds in the both cases. Only 2 double bonds in both the cases. That means one double bond got reduced. One double bond got reduced. So in the Birch reduction, one double bond get reduced. Okay. So how you can see that this position of the double bonds in both the cases are different. So that means we have to understand this only, that how this position of double bonds is different in both cases. So in the case of electron donating group, that is the first case, the double bond, this double bond would be very near, or would be very near to this electron donating group. To this electron donating group, this double bond would be very close. But in case of electron withdrawing group, that is the COOH, this double bond would be far from this COOH group. Like see, here we have 1 carbon difference between the double bond and COOH, between COOH and double bond, while in this case there is a no carbon difference. There is a no difference. That means in OCH3 such kind of final product would be there, and in electron withdrawing group such kind of product would be there, and the mechanism we will see in the next slide. Okay, so hope that this you had understood. Okay, so now move on. So this is the mechanism. So you see, this is for the electron. This is for the electron withdrawing group. Here we have electron withdrawing group. So what happened? Homolytic fission would occur. Homolytic fission of this double bond would occur. This double bond will cleave homolytically, and one electron goes to this carbon and one electron goes to this carbon, and this carbon will get reduced by this electron. This carbon will get reduced, and this electron is actually coming from this sodium. What I had told you, that this sodium liquid ammonia will form a solvated electron. Alright. Now this electron will goes to here, and this carbon get reduced, and you see this, there is a negative charge here, and it is radical here. Okay. Now again this negative charge will attack to this hydrogen of this amine group of this ammonia. This negative charge will take up the electron and form this, and actually this double bond again cleaved up, and here radical will come out, and see here this radical is here, this radical is here. Okay, so this radical and double bond would form. Okay, now one thing what I had written in the previous slide, see, radical and electron should be as far as it is possible. In the mechanism we have to kept the electron and the radical as far it is possible, and the condition is that negative charge would be at this carbon and the radical would be in the para position, would be the favorable condition. Okay, so this occurs, this happens. And the second thing that I have written here, that if we have electron withdrawing group, then we must keep the electron near to it and radical as far to it. That means if we have a electron withdrawing group, that means COOH group, then we have to keep the negative charge very close to the electron withdrawing group. That's why I had made the negative charge, the electron attack to this carbon, because here negative charge is very close to this COO minus group. Okay, I hope that you have understood this thing. Okay, now what will happen again, this radical point will get reduced by this electron, okay, and we will end up with this, we will get this one, and this negative charge again attack to this amine hydrogen, and it will give us the final product, this one. This is our reduced product. So this whole mechanism can be understood in a very short trick way that I had told you earlier. Like if you have electron withdrawing group in your ring, then you have to place the double bond in this manner. Okay, you have to place the double bonds in this manner. All right, now let's talk about, or say let's see the mechanism of the substrate where we have electron donating group in the as a substituent in our ring. Okay, now we will be having sodium liquid ammonia. Okay, so it will give us one electron. Okay, and this homolytic fission will occur, and what I told you, that you have to keep the negative charge close to the electron withdrawing group. That means you have to also need to care about negative charge should be away from electron donating group. Okay, you have to keep the electron away from the electron donating group. So how this mechanism will go, see, OCH3. So here you will make a radical, the radical comes out to here, and negative charge will come to here. Again this will go in the resonance, and you will get this product. So these are the resonance structures that you can make by your own. I here assuming that you people are knowing how to write the resonance structures. Okay. Here I am getting little bit stuck because I had approaching the question in a little bit different way. Okay, so let me do it in a different way. Okay, okay, this homolytic fission will occur. We will kept this negative charge very far from here. Okay, so this resonance will occur. Now you see that this is the radical and this is our. Okay, now the it will attack, this negative charge will attack to this proton, and the reaction goes in this way. The reaction goes in this way. Here the radical is there. Okay, and now proton comes here, and again the electron will attack to here, and this kind of reaction would occur. Here negative, here proton, again NH2H, and this proton attacks, and you will get this product. You will end up with this product. Okay. Okay, wait. Okay, so basically this product you will get. Okay, so in short, I can write what I had told you in the first slide. In the first slide, this is the overall conclusion of this long mechanism. Okay, this is the overall conclusion of this long mechanism. I hope that you had written down all of the concepts in your notebook. One more thing, that if you have a question like this, then what you will do? COOH and OCH3. Both substituents are present in your substrate, and you have to carry out the Birch reduction. Then how you will proceed? Tell me, otherwise I am telling you. And try to do it by your own. At least you have to try. Okay. So you know very well that in this case, if only electron withdrawing group is there, then it will give such kind of product. Okay. While if you have electron donating group, then you will end up with this kind of product. Alright, now if you have both, then what you can do, you have to put the double bond positions in that way. In the sense, see how I am going. OCS3 is there, OMe is OCS3, okay, because it has not sufficient space. Okay, let me make it in the next slide, okay, so that you could able to understand very easily. So our reaction is COOMe. Here we have OMe. Okay, so how we have to do? We have to maintain the double bond position. Oh, I had made a mistake. Here COOH. Here it is COOH. Okay, so COOH and OMe. We know very well that in terms of COOH, we have to make the double bond in this way. Okay, Also, we know very well that in terms of OME, we have to make the double bond in this way. What? In this way only. So this is your final product. Your product would be this one. Now, I hope that you understand that in terms of COOH, you have to make the double bonds by one carbon difference. While when you have electron donating group, you could not have to. You have to make the double bond at that carbon only. So see, we are both the conditions are satisfying in this compound only. Both the conditions are being satisfied. Okay. Now I have a different question. See, COOMe is also an electron withdrawing group. Okay. Now if we have NR3 is electron donating group. Now you have to carry out the same reaction. Okay. Now how you will go? Try by your own. Then I am telling you here, but try it at least once. Try by your own. Okay. So you know very well that for COOMe you have to make in this way, and for NR3 you must have to make. I am just making it by dot. You just have to make at here. Okay. So both the conditions cannot be satisfied. In this molecule only. So just I am reminding you what I had told you. That you have to see the electron tendency, or say your electron withdrawing group that you have in your molecule, because overall you have to maintain and stabilize the electron density, that is the negative charge. You have to stabilize the negative charge. So electron withdrawing group stabilize the negative charge. That is why your product would be according to the electron withdrawing group. Okay, your product would be according to the withdrawing group, and that is why this would be your product. That is why this would be your final product. Okay. So I hope you people had enjoyed and understood the concept very well. So see you. Have a good day. Bye bye.